Hello everyone. In this video, I want to talk about a very important optimization technique called particle swarm optimization, PSO. And this is really good if you want to do a global optimization. What does global mean? Global means your function can have a bunch of local minima and some global minima, one global minima and a few local minima. And the goal of this technique, methods like this, is to find that global one and not get trapped in the local one, right? So if you have a function that looks something like this, you don't want to find these guys. You want to find this one. Okay, now, is that guaranteed? Not necessarily, but the goal of this method is to find it. So many of the functions that you use in MATLAB optimization toolbox, like fmin_con, fsolve, or fmin unconditional, right? So this is with condition, this is no condition. These guys typically are local optimizers. But there are ones like particle swarm, like genetic algorithm, like simulated annealing, and pattern search that can look for the global one. And these are very important, especially when the dimension of the variables are going to go up. So you don't have a single variable function, you have a multi-variable function. The regions that you will get can be very complicated. You can easily get trapped in flat plateaus. You can easily get trapped in a local minima, and getting to the global is not a trivial task. So let's look at this algorithm, and hopefully in a few other videos, I talk at least about one or two of these other algorithms too. So the good thing about this is inspired by nature. You can see that, for instance, if a flock of bird or a school of fish are looking for something, not only each one of them is looking for that, they also look at the other ones and see if any of them has found what is it that they're looking for, whether it's food or anything else. And so their behavior, their search behavior, is not only depends on their own personal perception, also depends on whether there is one in the group that says, hey, I found it, this is it, it's here, then everybody goes toward that. Okay, so there is a personal best or search, and there is a social or global best that the whole swarm, one of them can find. And if one of them can find something that is better than everything else, then they all try to move toward that global one, while also trying to look around themselves too. Okay, so that is the beauty of this method. The other thing, so it's first of all is population based, okay, or we call multi-agent, multiplayer, multi-solution. So you don't have one particle that looks for the global minimum. You have several of them. Several players at the same time are trying to find this global minimum, and the goal is how to guide all of them toward this. The other thing is it has some stochastic component to it. So when they move around them and they try to find the minimum, although their motion is guided by how much the function is going down and the global behavior, there is also a little bit of randomness component, so they can explore the region a little bit better and not be trapped. And we're going to see that. Okay, so multi-agent, stochastic global optimizer, which is inspired by nature. And it came out, I guess, in 1995. And this is a really powerful technique. So you see that most of the things that I said are also covered in this basically table here. Okay, so as I said, they try to find the global one, but they cannot necessarily guarantee it. Okay, these local ones, they will always guarantee to go to a local minimum under, of course, some condition. These guys try their best. So let's talk about it. So here, if this is the position of particle I that is trying to find the global minimum, or particle j actually, this is particle j at iteration I. If this is where it is right now in the basically multi-dimensional space of search, and this is where it's going to go in the next iteration, how is this motion going from j index I to I plus 1, how is that going to happen? Well, it is guided by the velocity component of it. If the velocity that it gets is vi plus 1, I can say that because I know the velocity and I know my initial position, I can find what my final position. So this part here is like pure kinematics that you learn in a dynamics course, right? So if I know my position at iteration or at time t and I know my velocity, then I can find my next position. Now, you know, in dynamics, we always multiply this by a delta t as well, but here, my delta t is just t here represents one iteration. So in this case, this delta t is a 1 because you go from one iteration to the next, so you don't need it. And basically, this v here counts as a displacement and also a velocity. Okay, now the question is, how do you determine this velocity? How do you determine how to go from xt to xt plus 1? Well, this velocity, if you look at it at this iteration, comes from three components. The first one is, it is gonna be affected by how much it moved in the previous iteration. By the previous velocity, it is gonna be a component times that, and this W is what we call inertia weight, right? Or momentum. So basically, if the particle, let's say if this specific particle was going in this direction in the previous iteration now, and it's here right now, because it was moving in this direction, it is going to get what? It is going to get a small fraction of that previous motion to keep its momentum, okay? So this is the inertia or the momentum here. That is one component of it. And it helps not being trapped in a local minimum, or if you are on a kind of flat surface or plateau. The other thing it has, this is the part that all of the optimizers do. This is the local search for that particle. It says, hey, based on where you are and the best thing that you can have locally, right, the local minimum that you have, try to move from where you are to the best local minimum that you can find. Now, there are two weights here, C1 and R1. This C1 is called the acceleration coefficient. So the bigger it is, the bigger this local minimum is going to affect the change in the velocity. Okay, this extra component will affect it more. The other thing is this parameter R, which is your random parameter. This comes from a uniform distribution between 0 and 1. If it was 1, that means it's perfectly affected by the relative position or the displacement vector between current and the local best. But here I put a randomness to it. And this randomness is between 0 to 1, so it's not going to be entirely affected by that, just partially. And that is the random components. And the good thing with this is it helps your particles scatter around more the search space and look at different diverse directions so you can do more exploration. Okay? So this is your local best. And also you have a global best. So if one of them found a global best, you also will be affected by going from wherever you are to this global best, multiplied by its own coefficients of acceleration and multiplied by its own random number. Okay? So wherever you are affected by your previous motion, by your local best, and by the global best. And where does the global best come from? Well, it might not exactly be this. At the moment, your global best could be the best that all of the other particles could find. So maybe at the moment, the global best is not necessarily the perfect global minimum. Maybe this point here is the best that was found here. So you will be affected by this. So you see that these particles need to communicate with each other so they find which one of them has the best of all at the moment. Okay? So this one needs some communication and finding the best of all particles. So these three components together will determine how much you move. And you can see that effect over here as well from this picture that I downloaded from this website explaining the PSO. You can see that this yellow vector is affected by what? Is affected by a component of the previous motion, this purple vector, based on where the local best is for you, it is affected by this green one, which tries to take you to the local best, and it is by this red vector, which tries to take you to the global best. Okay? So the sum of the purple and green and red, which is these three vectors, that is going to be your equivalent velocity at that point. Okay? And of course, by changing the weights of W, C1, and C2, you can increase or decrease the role of each one, right? And we're going to talk a little bit about how to tune or set those parameters or what numbers to pick for W, C1, and C2. R1 and R2 in each iteration, they are coming from a uniform distribution. So each time they are a different number, and that helps them scatter around, move around, and hopefully by all of this extra random motion, you can ultimately get to where you want to get. Okay, so this is the pseudocode for it, and you can see that's basically what I explained. And this one coming from Wikipedia. Okay, so that's not my picture. And now let's talk a little bit about these parameters. So most of the algorithms, if you look, they typically set the C1 coefficient, which we call it cognitive coefficient or local, and C2, which we call it the social coefficient, which comes from the global best. They typically put them in a range of 1.4 to 2.2, and many of them, they typically start both of them at 2. That's 1. 2, what about the inertia weight or the momentum part? Typically, they started like something like 0.9 or so, and then as you go toward the goal, they try to reduce that. Because once you get close to the goal, you want to kind of settle down. You don't want to be too much affected by your previous motions much, okay? And you want to settle, because if you don't, now you reach to this point, now you're going to go uphill. So you want to reduce the amount of inertia as you get toward the global minimum. So you can have a gain scheduling, right? And change that maybe linearly over time or versus iteration or something and reduce it over time, okay? The same goes for a learning rate in gradient descent that you define a gain scheduling for it. What about the number of particles? How many of these participating particles, how many of them would you use? Well, of course, the more you use, the better chance of finding the global minimum, but of course comes with it a lot of computations. So many problems, we go with something like 20 to 50 particles. If the dimension of the search is very large, so you don't have 2 or 3 variables, you have 10 variable, 10 dimensional space to search, and there might be lots of multimodal cases, you definitely want to use more particles, okay? So your particles are not super sparse in your environment. Okay, another thing you can do is to put some threshold on these velocities. So whatever velocity that you get when you calculate it from this formula, you might want to put some threshold on it, okay, or saturation, and don't let it to get much bigger. Why? Because if it does, it can get completely out of your search region, okay? So you typically limit it to only be a fraction of your domain size to make sure that it doesn't go crazy and diverge. So you can put some threshold on the velocity called clamping. The other thing you can do is use several restarts. So start with one set of particles, 20, 30 particles, let's see what they do, and then start it again. And the important thing is this. The question is, where do you put the particles in the beginning? So when you start these particles, where would you put them? The answer is random. In the beginning, your position of the particles and their velocities are all what? Random. Then they start changing based on this rule. So when you restart it and you have a random start, then you're probably gonna get better job, and you might use statistical performance methods to make sure that you are getting to a better performance. Okay. So final things I want to tell you before I show you the MATLAB code is, one thing that you want to do is, if you have several variables and they have different ranges, so for instance, your function that you are trying to minimize is a function of x1 and x2 and x3, and x1 only changes from -2 to 2, x2 is, let's say, -5 to 5, and x3 is, I don't know, -20 to 20, because one of them has much bigger numbers than the other ones, and that will dominate the change in the function. One of the things you want to do is to normalize the range of these variables, so your contributions from each variable is kind of close to each other, not one completely dominating. As I said, you need to tune those parameters, and I gave you an idea that what is it that they do. For W, you use some large parameters in the beginning if you want to explore more and then decrease it over time. For C2 and C1, depends on what you want to do. For instance, if you want to explore more, which means go around, scatter more, so you get a better chance of finding it, right? You might want to use a smaller C2 and a larger C1, okay? Right? And remember what C1 and C2 doing. C1 is your local best, is your cognitive one. When you increase C1, what's going to happen? Each particle will explore their own space independently. They are not going to be affected too much by whoever says, hey, I found the best one. They try to look around them. Maybe they have some very much better, much smaller number than that current global, and they try to, each one of them, search their own area before going toward the best of the swarm, okay? So that is really good. If you set it bigger, you have a better chance of exploration. Now, if you make it very big, you might get divergence or diverse trajectories, okay? And if you make it smaller, of course, they all try to get toward their global. Similar thing for C2. If C2 is big, basically all of them try to get toward the current best from all particles, so they do not explore too much. And if you make it small, of course, they wander more. So you see C1 and C2, they have kind of opposite effect of each other. That's why you pick a big C1 in the beginning and a small C2. And as you go toward convergence, maybe you can change the direction of them. Let C2 be a little bit bigger, let C1 be a little bit smaller. And the same thing for W. So bigger W means larger exploration jumps, which sometimes might mean slower convergence, but smaller W means they basically follow the global and local best, and so they will not have the chance to explore too much. Okay? So this is a brief overview of particle swarm, how it works, and what is the update equation and the pseudocode here, right? And I want you to pay attention to here. Look. So for each particle, look, from t to max number of iterations, for each particle, first you update the velocity. You're gonna clamp the velocity to make sure it doesn't go out of the bounds. You update the position. You make sure that this new position you get for the particle is within the search region. because so far we did not put any limit on search region. How far is x1, x2, x3? They are not typically infinite. So you need to make sure if you get a new position for any particle, it is within the bounds of the position. If not, you have to recalculate it, and you have to evaluate f for the function you are trying to minimize for each and every one of the particles. If your current particle, f at the current particle, is better, and here better could be minimum or maximum, which means less than or bigger than. If it's better than the best that same particle had, go ahead and update the best of that particle. And if the best of the particle is better than the global best, then update the global best. You see, so this is the part that the communication happening between the particles. Okay? And you can update your W, you can even update your C1 and C2, and at the very end, return what? Return the GBest. Okay? Right? Which is the variable, independent variable, and you can also return the F at the GBest. Okay? So now let's look at the MATLAB code here. So here there are two different ways to run this code. The function that is used is called the Ras-Riggin function. Hopefully I pronounced the name correctly. This is a benchmark function that is not easy to find its global minimum because it's a non-convex function, and it has, as you can see, if you look at that, so you see 10 length of x, sum of x squared, 10 cosine of 2 pi x, right? So you see that the shape of the function is not such a nice function because there is a sum to it, sum x squared, and there is 10 cosine of 2 pi x, and there is a sum and 2 and 10 length of x. So it's a very, very nonlinear function, non-convex, and finding the global of this is absolutely not an easy search. So in this case, we only use two variables, x1 and x2 in it. So it's a 2D or 3D search. The function is a function of two variables. The region that we are going to search, you see here the dimension is 2. The region we are going to search is between negative 512 and positive 512 for both left, right, up, and down. The initial weights for inertia is 0.9. Then we go down to 0.4. The maximum number of iterations we are allowing is 200, and the number of particles is 40. C1 and C2 we start at 2, and you see that V max is 0.2 max minus min, which is about 0.2 times almost 10, so it is about 2. So no V, when you update V, should be ever bigger than a 2 or a negative 2. Okay, and you see here I'm starting the positions by what? By random. You can clearly see that, and all the velocities as 0. You don't need to have both of them random, but positions definitely random. Velocities we start at 0, and then we keep going. We don't have any idea for V-best, P-best, and global one. The global one for now, we just run a min over all of them. And then here, this is the code that keeps running it and also animating it. Okay, so if I run this portion for you, you can exactly see the behavior of that. Let me run it. It's very nice, actually. There we go. Look. So your function that needs to be minimized, you can see that, and the minimum of that is 0. It's going down, and look, all of these white ones are your particles. Again, look at this function. Look at the contour plot of this function. Right? It's not a regular function. It's an extremely non-convex. If you look at this guy in 3D, this is a very, very hard function to find its global minimum. And you see that the red spot here, that asterisk, is the global best. Each one of them is trying to find their local best, randomly moving. But ultimately, see, as it goes toward the end, they are getting closer and closer to the global best. And you can see that this guy is going down, down, down until the value of the function or the change in the variables falls below a threshold, and then it is going to stop, or it is going to go all the way to 200 iterations if it has to. So you see that the function is constantly going down, and ultimately the goal of it is to go to the absolute global minimum, which in this case is 0, and tell you where the location of that global minimum. You see here, there are only a few of them that's still searching. Most of them already said, well, I give up. I'm going to go with whatever the global best is. You see, even those are now giving up searching and trying to join the rest of the swarm. Okay, yeah? So you see that it is going all the way to 200. And if you give it more iterations, it tries to do even better. So this one does not stop anywhere. It just keeps going and finally stops at 200 iterations. And you can see that the location that you have is 4 e to the negative 10, 3 e to the negative 9, which practically is 0. So the global minimum is at 0, 0, and the value of it is also 0. Okay, so this function, it has the origin as the global minimum, but it's not, again, an easy function to find its global minimum because it has tons of local minima. So this is doing it with the pseudocode. So this code is written based on pseudocode. The other one is MATLAB actually has a built-in particle swarm function. Okay, it's this function here. And this function, you only have it if you have global optimization toolbox. It's not in every toolbox. Okay, it's only in the global optimization toolbox. If you have that, then you have this command. And here you provide your function, and you provide the number of variables, you provide the ranges, right, for minimum and maximum of the search region, and the options involves all of those parameters. And it returns for you the location of the best, the value of the function at the best, exit flag, which is 1 if it successfully converged, 0 if something else happened, and output which has a bunch of information in it. I can show you if you want. So here, look, this function, you are saying that your optimization function is the particle swarm. The size of the swarm is swarm size, which in this case, I'm using the exact same parameter, 4D. And then the maximum iteration is max iter, which again is 200. Display the iterations. The inertia range is between W end and W start, right? And you provided them here. So they go from 0.4 to 0.9. Self-adjustment weight, okay, this is the cognitive one, is C1, and social one is C2, and you provided them with the same number as previous one. And then you have an output function. This output function allows you to send out the values that correspond to the location of those particles at each iteration and the best value of the function at each iteration. Because if you don't use this function, if you just ignore this part, what does it do? When you pass the function, the dimension, the options, lower and upper limit, what does this function do? It just gives you the final result, which is x best is 0, 0, and f best is 0, done. It does not allow you to read those intermediate values of the particles at each iteration, so you cannot animate it or you cannot plot anything. It just directly gives you the final answer. So in order to get those intermediate values, you get this output function, and in this output function, you try to save those intermediate variables so you can generate a plot, animation, or anything. So if you look at this here, you can see that in this function that I added, you are trying to what? You're trying to save those intermediate variables. First, you say, hey, I don't want you to stop right now. Go ahead and get the state of the solver and see what state the solver is in at the current iteration. This state that you pass to it can have 4 different types of values. It could be init, which means it's the first iteration. It could be done, which means it's over. It could be iter, which means it's somewhere in between, it's still working. Or it could be interrupt, which means some interrupt happened and the optimizer stopped. So it says if the state compared string is iter, which means your state is in the iter position, then go ahead and add to the iteration counter. And then if it's less than the maximum iteration, go ahead and get the optimum values dot best val and save it into this variable called history. And history is what we're gonna plot. It's a variable involving all of the best values. So we store it at the current iteration counter, and we're gonna later we are going to plot it here. Look, you see that here I get it recorded, and if it's not empty, I'm gonna plot it. Okay, so that's all it does. It doesn't have animation, but again, it at least plots the change of the best value over iteration for me. So let's go ahead and do this part. So here I'm gonna clean it up, and then I'm gonna use the built-in function here, and let's run this. And it is optimized and goes typically very fast. And look, here is the value of the best over iterations, and you see in like 79 iterations or so it converged actually by some threshold for how much it can change from iteration to iteration. So if the change in the variable or the function is below some threshold, it is going to stop and it doesn't go all the way to max iter. So you see that it started about 3839 and went to, as you can see, almost 0. You see it's something 10 to the 9, 310 to the 9. Okay, and it can give you this information. Look here. You see that all of this intermediate information, they are all taken from that output function. And as you can see here, they are all printed using the fprintf. You see here, so you have the best value, you can get min, you can get so much extra information, but at the end of the day, it says, hey, this is X best, this is F best, and I got it in 79 iterations, and this is your plot here. So I'm going to share this MATLAB file with you, which again has a built-in function and the normal code using pseudocode, and feel free to play with it and learn with it, change these parameters, see what it does, change the function, and hopefully you could understand how particle swarm is working. Thank you so much. I'll see you in the next video.